So, we would continue with the development of momentum integral equation, which I am spending so much time on it because conceptually it should be very clear in terms of the different contributions of momentum through the control surfaces in a flow field, because once these concepts are clear, you should be able to handle problems which are slightly out of the ordinary, and you would be able to use your concepts in those problems to obtain solutions to even more complicated problems than what are discussed in some of the textbooks. So, what we have shown here is that starting with the momentum equation and with the imposition of the conditions that these are steady two-dimensional flows, constant property, we identified what are the forces on the left hand side of the momentum equation. The forces on the left hand side of the momentum equation, they constitute of body force and surface forces. We have assumed that there are no body forces present in the system. So, if I write the equation for the x component, what I have is f s x is equal to, since it is steady state, the first term on the right hand side would be 0, the del t term would be 0, and what I have is the net efflux of momentum into the control volume because of flow. So, f s x, when then we have drawn a control volume ABCD, where BC is located very close to the edge of the boundary layer and AD is located very close to the solid liquid interface, very close to the solid plate. So, what I have is MF, the momentum flow through surface AB, BC, CD and AD. We have also identified that when we talk about the forces, since only the surface forces will remain on the left hand side of the equation, what could be the surface forces? We realize that these two surfaces AB and CD, they are being perpendicular to the direction of flow, they are exposed to pressure force. This surface AD, which is parallel to the flow direction, it will not have any force in the x direction, any force due to pressure in the x direction, whereas the surface at the top BC, which is slightly curved, will have an x contribution of force. Since the surface is curved, the force which is acting on this curved surface multiplied by the projection of this curved surface in the x direction would give me the force which is force due to pressure on surface BC. And we have also understood that on surface BC, if you again look at the figure, the surface BC being very close to the edge of the boundary layer will be devoid of, will not contain any velocity gradient. If it does not contain a velocity gradient, then the shear stress would be equal to 0. So, on three surfaces, two sides and the top surface, pressure forces will act. On the bottom surface, there would be no pressure force, only a shear force would act. If I assume that the pressure at the left edge where the flow is coming in, if the pressure here is P and the thickness is delta, the depth is Z, dz, then the force on this surface AB would simply be equal to P times delta times dz. Let us assume that the surface at the other end, the vertical surface at the other end CD has a pressure equal to P plus dP dx evaluated at x multiplied by dx, which is nothing but the Taylor series expansion of whatever be the pressure at this point. So, this is the pressure. What is the thickness over here? It is delta plus d delta. So, the force acting on surface CD would be pressure which is the Taylor series expansion of pressure over here, the area would be delta plus d delta multiplied by dz. So, those are the two pressure terms which we have identified. The curved surface, the projection of this curved surface in the x direction is d delta, the depth of it is dz. So, therefore, the area which would contribute to an x component of pressure force is simply going to be d delta times dz, and the pressure which is acting on surface BC can be approximated as the arithmetic average of the pressure at B and that at C. Pressure at B is P, pressure at C is simply the Taylor series expansion. So, the average arithmetic average pressure on surface BC multiplied by d delta dz would give us the x component of pressure force acting on surface BC. The only other thing which remains is what is the shear force on surface AD, the surface AD which is located very close to the solid surface. Now, we are expressing it, the force on surface AD as minus of tau w times the area. What is the area? The length times the depth, dx times dz. So, minus tau w times dx dz would give us the shear force acting, the x component of the shear force acting on surface AD. Why this tau w and why this minus? Tau w is introduced because tau w is the engineering parameter that we would like to know. What is the shear stress expressed by the moving fluid on the solid object is the second criteria, second point of our interest. Our first interest is to obtain delta as a function of x. The second, probably more important, is to find out what is the wall shear stress, what is the shear stress experienced by the solid object when there is a relative motion between the fluid above it and the plate below. So, tau w is the force experienced by the solid, but when we think of the control volume of the fluid, we need to find out what is the force on the control volume. If the force experienced by the plate is tau w, then the force experienced by the fluid above it must be equal to minus tau w. So, the force experienced by the control volume due to shear in the x direction would simply be equal to minus of tau w multiplied by dx dz. So, now we have all the terms present in order to be used in the equation of motion. All the force terms, 3 pressure and 1 shear, and on the right hand side we have all the momentum flow, the momentum that comes into the control volume because of flow. So, all the terms are in place, you plug in, put in the term of the equations, and then you simplify. I will not do the simplification process in here because no additional concepts are involved. It is only an algebraic manipulation of these 6 or 7 terms in order to arrive at the final form. So, that part is done in your text, but since nothing new in terms of conceptual clarification is required, I will not do that in the class. You can take a look at your textbook Fox and MacDonald, where this has been done in great detail. So, what I am going to do is I am simply going to write the final form of the simplified equation when all these considerations are put into place, and what we are going to get out of this is known as the momentum integral equation. So, I think conceptually it is clear how it is to be done. The only thing that remains is to put those terms, simplify them, rearrange them, and get the final form of the equation that I am going to write now. what you get is tau w by rho is equal to d dx of u square theta plus delta star u du dx. This theta, I think you will recall, is the momentum thickness, which is defined as Vx by u 1 minus Vx by u times dy, and delta star is the displacement thickness, which was defined in the following form. So, this is the all important momentum integral equation. So, what is then momentum? What are the salient features of momentum integral equation? That it relates the wall shear stress with the momentum thickness, with the displacement thickness, and variation of the velocity and variation of the free stream velocity over x. So, points to note here is, first of all, this gives an ODE. Unlike the analytic approach we have used before, we have seen before, this equation gives rise to an ordinary differential equation and not a partial differential equation, which is a huge improvement of our previous approach, that we deal with an ordinary differential equation. The second one that you would see is that the wall shear stress appears in this expression, and we haven't made any suggestion that whether it is going to be, what is the relation between tau w and the velocity gradient. So, it is open to Newtonian as well as non-Newtonian type of flows, and since the relation between tau w and the wall shear stress are not specified, it can be used for laminar flow as well as for turbulent flow. So, the expression of without, since the specification of the wall shear stress is not there, therefore, it is equally valid for turbulent flow as well as for laminar flow. Okay. So, this is the equation which we are going to deal with in our subsequent analysis. So, but even then, I would just like to work with me for a few more minutes and see how this equation can simplify of what we know about flow in a boundary layer. The analysis, the derivation of this may be involved, but what you get at the end of it is a compact expression. And anytime you propose something, you have to benchmark it. You have to prove that what you are saying is correct. And how do you prove that? You must compare it with the results that are already known to us. So, what is the result which is known to us, on which we have sufficient, we know it to have sufficient confidence that the result is correct? We have an analytic solution followed by a numerical solution for a very special case where there is flow over a flat plate with 0 pressure gradient, a Newtonian fluid, laminar flow. And we know what is the expression for delta as a function of x. We also know what is the functional form of the friction coefficient for such a case. So, the first thing one should do is to apply this momentum integral equation to that problem and see if you are predicting results which are close to that of the result for flow over a flat plate, 0 pressure gradient, steady laminar case. So, that is what we are going to do, and while doing so, it would be clear to us how to handle this momentum integral equation, and I can assure you that by the end of this chapter you will all be experts of using momentum integral equations in much more complicated cases. So, always start from the basic, think about the assumptions which are used, think about the, if you do not assume it, at which point you should start in order to obtain a solution for the case. But right now let us see how we can use this equation for the simplest possible case. So, we start with the simplest case where we have the use of MI equation, 0 pressure gradient flow, and we have tau w, the full form is d dx u square theta plus del star u du dx. So, we are using it for flow over a flat plate. The moment we say flow over a flat plate and it is a 0 pressure gradient flow, we understand that u is a constant. So, for flow over a flat plate, as we have seen before, and for 0 pressure gradient flow, u is a constant. The moment u is a constant, this equation will simply revert to tau w by rho. Since u is a constant, u can be taken out and d dx of theta, and this term would be equal to 0. So, for this situation where we have a flow over a flat plate, 0 pressure gradient, this would be the form of the equation, and tau w by rho would be equal to u square times d theta dx equals tau w is rho u square d dx of 0 to delta Vx by u 1 minus Vx by u times dy. So, this is simply the definition of the momentum thickness. So, we have it up to this, and then we continue. And we will say that y by delta is equal to eta, where we are done, since the velocity in the previous equation, the velocity is dimensionless, since we are dividing velocity, local velocity, by the free stream velocity, which is a constant. So, we are dividing y by delta in order to dividing y by delta in order to bring in a new variable which we call as eta, and therefore, the limit from 0 to delta, since we are dividing it by delta, it would simply be equal to 0 to 1. 0 to 1, the Vx by u will remain unchanged, 1 minus Vx by u, and from dy it simply would be d eta, and therefore d eta, and I bring the delta outside where I have the d dx as well. Are the steps clear? First of all, from the previous expression, I see that the velocity is dimensionless. So, it was y there. So, I am going to change y to a dimensionless variable eta. So, I divide both sides, I divide it by delta, and this is just a definition. So, therefore, dy would simply be delta times d eta. Delta is the local thickness of the boundary layer. So, to the previous equation, I substitute, instead of dy, I substitute delta times d eta. So, delta times d eta. So, delta can now be taken outside, and I would clearly write it rho u square d delta dx 0 to 1, let us put it inside a bracket, Vx by u times 1 minus Vx by u times d eta. Now, if you look at the third bracket, this one in here, it is a definite integral. If it is a definite integral, then what you are going to get out of this is a constant. So, your tau w would simply be equal to rho u square d del dx times beta, where beta is simply a constant. This beta is this one. Now, therefore, in order to do this, one must know what is Vx by u as a function of eta. If I can find out, if I have some means to find out the variation or the dimensionless velocity as a function of eta, then by substituting this functional form in here, I should be able to obtain the numerical value of beta. And I am integrating it from 0 to 1, I am integrating it over a fixed interval. So, what I would get out of this is just a constant. So, the only job that one has to do in solving a problem with momentum integral equation is to suggest what would be Vx by u, what would be the profile of Vxu in terms of eta. Now, one can choose a linear profile, a parabolic profile, a cubic profile, or some other profile. Surprisingly, you would see that the results are going to be very close to the one that we have obtained from the Blasius solution. Why? That we will discuss later. But let us start with some assumed profile of Vx by u in terms of eta, the dimensionless distance, and let us first assume it is to be a parabolic profile. So, Vx by u is equal to a plus b eta plus c eta square, where a, b and c are constants. Whenever you propose such a profile, you must have a way to evaluate a, b and c. So, how do you evaluate that? In order to evaluate that, you should know Vx by u or the variation of Vx by u at different values of eta. Remember again, eta is y by delta, and y is the distance from the solid plate over which the flow takes place. So, what is the condition on the solid plate? Vx is 0, no slip condition. So, you can say that eta equals 0, Vx by u is equal to 0, first condition, but you need two more to obtain what is going to be to obtain the values of the other two constants. What is the other boundary that you can think of, where it is the edge of the boundary layer, and what happens at the edge of the boundary layer? What is going to be the value of Vx by u at the edge of the boundary layer? It must be equal to 1, since Vx is equal to u at the edge of the boundary layer. And secondly, another factor another characteristic of the profile that you know is that's going to happen is that the gradient of the velocity with respect to y disappears when y is equal to delta. When y is equal to delta, eta is equal to 1. So, at eta is equal to 1, Vx by u is equal to 1, and del y of Vx by u is going to be equal to 0, since the velocity gradient disappears at the boundary layer. Let me write it and it would be more clear to you. So, what I am proposing is that Vx by u is equal to a plus b eta plus c eta square. So, I therefore need boundary conditions. So, what I am saying is that at y equals 0, Vx is 0, at y equals delta, Vx is equal to u, and at y equals delta, del Vx by del y is equal to 0. So, you can convert them to in terms of eta as well. So, what it essentially tells you is that eta equals 0, Vx by u is equal to 0, at eta equals 1, Vx by u is equal to 1, and at eta equals 1, dVx by u by d eta is equal to 0. So, these are the conditions which are to be used with this equation to obtain the values of A, B and C. So, when you evaluate the values of A, B and C utilizing these fundamental physical relations, what you get is Vx by u to be 2 eta minus eta square. So, where eta is equal to y by delta. So, now it becomes pretty straightforward. My equation was for the flow of a 0 pressure gradient flow, tau w by rho is d dx of, or rather u square is outside, times theta, and which would again leads to, when I express it in terms of dimensionless quantities, tau w is equal to rho u square d delta dx 0 to 1 Vx by u 1 minus Vx by u times d eta. From our assumed profile, I know what is Vx by u. I put it over here and I put it over here as well. When I assume that it is a Newtonian fluid. If it is a Newtonian fluid, then tau w is simply going to be mu del Vx del y at y equals 0. When you use this over here, you would simply get is to be equal to 2 mu u by delta. So, your tau w is now becomes equal to 2 mu u by delta. What you have is rho u square over here d del dx, and when you perform the integration over here from 0 to 1, this becomes 2 eta minus eta square, and this becomes 1 minus 2 eta plus eta square times d eta. Perform this integration. I will not do it over here, but what you would get is simply 2 mu by delta rho u is equal to 2 by 15 d del dx. Remember, since this is a definite integral, you are just going to get a constant, and which turns out to be equal to 2 by 15. So, your choice of Newtonian fluid and your choice of any arbitrary profile has given rise to a compact ordinary differential equation connecting delta with x in terms of the properties mu and rho, the unknown delta, and the condition and the flow, the free flow, the velocity at the outside of the boundary layer. So, you integrate it once, and what you get is del square by 2 is equal to 15 mu by rho u times x plus c, where c is the constant of integration. So, at x equal to 0, at the edge, at just the beginning of the flat plate, at x equal to 0, delta, the boundary layer thickness is 0, which would give rise to c equals 0. So, therefore, when you substitute it, is equal to 5.48 by root over r e x. So, this is the thickness of the boundary layer as a function of axial distance, thermophysical properties, and so on. And even if you look at the expression of Cf now, which is friction factor, tau w by half rho u square, which would be 2 mu times u by delta divided by half rho u square, and it would be 4 mu by rho u delta and when you substitute the expression for delta in here, you get Cf equal to 0.73 by root over Rex. So these quick solutions give you the growth of the boundary layer and what is the friction coefficient. If you do not remember this, if you do not remember, I am going to use what we have done in Blasius solution, what we have obtained in Blasius solution. Delta by x was 5.0 by root over Rex, and from Blasius solution we have obtained 0.664 by root over Rex. That is the beauty of it. See, the form of the two equations are identical between a method which is integral, which is easy to use, which does not assume most of the things that are required in Blasius solution, where the solution is so simple and you get a relation of delta which is only 10% different from that of the exact solution of Blasius, coupled with the numerical solution by Haworth, and this is 0.73 and this is 0.664. So if you just look at these two things together, they will highlight the utility of momentum integral equation. That means you are getting two cases. One is so complicated to use, you are working with PDEs, you are working with numerical solutions, and the other you are working with an ODE which is versatile, which is easy to use, and at the end both are giving you almost same results, same form, and almost same values, numerical values. So definitely momentum integral equation is the method of choice for solving flow for boundary layer problems. And later on we would see how this equation, momentum integral equation, can be used for other type of geometries as well. But at the end of the day, still the question persists: why was momentum integral equation successful in getting a result which is within 10% of the accurate result by Blasius? What is the secret of the momentum integral equation? The secret lies in the fact is that we are dealing with a very thin boundary layer, and in a very thin boundary layer, if you can correctly identify what is the boundary condition on the solid plate, which is no shear, and what is the condition at the edge of the plate, that is the velocity is equal to the free stream velocity and the gradient of the velocity is 0. So you have identified three boundary conditions at the edge of the boundary layer and on the surface, and the entire thing is very thin. So if in a thin flow domain your three boundary conditions are correctly specified, then no matter whether you take it as a plus b eta plus c eta square or a plus b eta cube or any other form, the chances are that it is almost sure that you are going to get results which are going to be very close to the differential approach. The differential approach, the velocities etc. are going to be valid at every point. In the integral approach, it's not accurate, but it is so easy to use. Since momentum integral equation is an order of magnitude simpler to use, and it is not restricted to the type of flow, unsteady flow, presence of a pressure gradient. So it's a flexible equation to begin with, and depending on the complexity of the problem that you are dealing with, you have to solve sequentially. But at the end of the day, it's an ordinary differential equation, unlike the Blasius solution case. So momentum integral equation is therefore the method of choice for handling most of the boundary layer problems. So in our subsequent classes, we would see the use of momentum integral equations for the most complicated case for turbulent flow as well. and see how good they can represent or predict the experimental results, and that would underscore the utility of momentum integral equation even more.